So hello everyone. So thank you very much for coming to Uppsala. And that's a big change for me. So I was just on Sunday, last Sunday, it's Xiamen. And you see it's very green, so plus 20 plus degrees. And now I come here, it's snow, and it's like 30 Celsius degrees drop in temperature. But I really enjoy it because I didn't see snow for 4 years. In Xiamen is too warm. I really enjoy this place and very happy that everyone could come here, and almost everyone, because we had also some Zoom speakers, of course. But this conference started 2 years ago. And now it's very nice to have it in person, finally. That's a big improvement, because when we were hosting 2 years ago, we could only listen to OLS on Zoom, right? And it was not as nice as meet everyone in person, discuss during coffee breaks. That's what conferences are for. We need to talk, to meet people face to face, and I'm very happy that it happened now here in person. And thank you very much, Roland, to actually taking in charge it. We'll also send to all the team later, of course. But basically, we also have between 2 years break, so it's a biannual event. We also have online webinars for usually younger scientists, postdocs, who actually develop the code so that they can show how to use it. And if you want to help with organizing, suggest some speakers, maybe a postdoc, or you want to be a speaker, please just contact me. We will try to organize this. And then we have online webinars. We post on YouTube the videos, which you can actually find on this website, which we also update with all the future events. So that's kind of a web resource for machine learning and quantum chemistry. We go beyond traditional symposia. And I am very happy to say, so stay after my lecture, you will know that we'll have a continuation. So in 2025, it will be also in person. We'll announce it after my lecture. And this way, maybe Les will be again there, maybe not, we'll see. It's a kind of a tradition that he was the first, but we'll try to make also selection of new speakers, of course. Now, back to actually my scientific talk. Before I talk, I want to thank my group, part of whom are here. So they are very young people, usually master, undergraduate students, PhD students. So that's always fun to come up with some crazy ideas that postdoc will be probably hesitant to do. So that's makes us to try to some crazy ideas, and also we want to make practical computational chemistry. So we want to break through limitations of traditional quantum chemistry. And of course, in this conference, you see that we already breaking through, so it's become a mature field. When I was starting 10 years ago, it was still on the rise, but that was our goal already back then. And we also want to provide tools to do this, to use these methods, and of course we need to show how to use these tools. So and that all comes in a loop, because we, when we teach, we actually learn what works, what doesn't work, and try to improve the methods and so on, right? Now, I'm showing always this very simple example, maybe too simple for this audience, but I also talk to experimental colleagues. That's a very nice example, because actually we all know that we can get many things just from theory, and just the one thing we need to do is, of course, solving Schrödinger equation. We can get very accurate results for small molecules like H2. If you run it on laptop, couple cluster, you can get these results very fast, but in comparison to machine learning, is still too slow, if you, even for such a small molecule, right? And we want to treat big molecules, so that's where we want to go. So we don't want to limit ourselves to H2. And I was working on some empirical methods from my PhD studies, And motivation was that to go to the big systems, even DFT is usually too slow. And these methods are still useful. We don't get coupled cluster accuracy, but they are very useful to get correct physical behavior and explain us what we want. So maybe we will not get this precision, but we'll get some correct, at least, position of the bond, more or less, for the computational chemist and for organic chemists. It may be enough, right, to get some ideas about the reactions and so on. Now, usually most of people in computational chemistry use DFT, and BCRIP is one of the most popular still. For many years, there are many more beta functionals developed, but if you look at the how functionals are popular, this is one of the most popular. And there is a shift to at least run single point calculations based on DFT calculations, but still most of computational chemistry is done with DFT. I always recommend to computational people to use coupled cluster, at least for the ground state. But for big systems, we go to some empirical methods. Now with machine learning, we don't need to do this. And in principle, if we have enough data and a proper approach, in principle, we can get as high accuracy as we want. We just need to train our potentials and models. And when we do this, of course, we'll get a much faster result, as accurate. So if you train on coupled clusters, then we'll just reuse this model for different simulations. So that's all obvious for this audience. And what we also can do, we can update and improve quantum mechanical methods with machine learning. And I think this approach is very well represented in this conference. So we saw many different ways how we can improve ab initio methods, and you can also improve DFT methods, and we saw some empirical methods improved. So our own approach is AIQM1, which is falling in this category. So we improve some empirical methods with machine learning. And the motivation is because some empirical methods are so fast and they provide correct physics for many properties. And this is, so there are many different methods and ways to do it. So there was perspective already 3 years ago, but many of the concepts remain the same. It was updated later to the whole book with 27 chapters and 65 authors, many of whom are here. And this book is very useful to actually educate people, because we provide also on GitHub and other platforms a course and source codes for some simple programs so that students can play with it. And basically, the concept behind this one is very simple. So it's based, so you can learn Hamiltonian. I will not talk about this. It was very excellently covered by Dave before, but I will talk about delta learning, because this approach is super simple, but it's very powerful. And the goal was, from already 10 years ago, that we'll try to achieve near chemical accuracy, 1 kcal per mole, general for different molecules, by combining classical quantum chemical methods with machine learning models. It took 2 years, and thanks to really very nice collaboration with Anatoly, who was pushing this project, with Raghu and Matthias, and this become now kind of a standard tool to improve methods. So delta learning is now very, very standard. But before, nobody believed in it, and that's why it took us 2 years to publish it. So the idea is very simple, but we showed, of course, that it works. And here is very simple explanation why it works. So if you look at H2 dissociation curve, then if you just train on these circle points, machine learning will be very, very accurate. So it's very nicely reproduced. And extrapolation is a problem for machine learning. While if you have Hartree fork, then or some empirical methods, they will at least give you very close minima, the position of the minima. But the accuracy is very terrible. So now if we look at the differences are much easier. They behave much smoother. And if you learn these differences, So you can correct a low-level method, which has correct physics, with machine learning, and it will be even able to kind of a bit extrapolate. So that makes the method very robust, and that's why delta learning is extremely robust approach to make it transferable, and it doesn't break down as simple as pure machine learning potentials. We generalize this to include like different corrections, because obviously you can benefit from combining many different quantum chemical levels. But back to this scheme, so I'm always saying that now current methods, they're out of the box already. So after 10 years, we have already methods which are applicable to simulate organic molecules without being retrained. So they are basically already general purpose and universal models. Like if you use BISRelief, you can the same way use our AIQM1 method by just swapping keywords from BISRelief to AIQM1. And it is 1,000 times basically faster because, well, it depends on the molecule, and the scaling is n to squared, while BISRelief is slower, while it reaches the accuracy of coupled cluster. So basically, I always tell that if you can use AIQM1, there is no reason to use the slower and worse methods. And this was become possible by combination of state-of-the-art semi-empirical methods with delta neural network correction, and we also added dispersion corrections, because neither neural networks nor semi-empirical methods are good at the dispersion interactions. And if you look at the timing, so it just takes 14 seconds on a single CPU for C60 molecule to optimize geometry, while DFT takes, of course, much slower, and at coupled cluster we can barely do like single points. That's why this method benefits a lot from the developments by many people. So they're based on Bella-Perinello neural networks, which we extended to ANI, and we use basically modified ANI neural network. It also benefits a lot from semi-empirical methods development, and we took the ODM2 methods, which I developed when I was postdoc with Walter Thiel. And this is really state-of-the-art semi-empirical methods, which covers not just ground state properties, but excited state properties at the level similar to TD-DFT. If you look at vertical excitation energy, they're very similar to popular TD-DFT. And we benefit a lot from data sets which are generated by Oleas and his collaborators. So we train this model on almost 5 million DFT data, and then we do transfer learning to 500,000 coupled cluster data to target the target cluster accuracy. That's our goal. So we don't want to target DFT accuracy, we want to go to coupled cluster accuracy. And I will show you later that it really makes a big difference. If you look at different benchmarks, some of them subsets of GMT-CAN55, you don't need to look at this huge table. You just need to look at the colors and see that AIQM1 is pretty much green, so it means its accuracy is very good for many properties. If you focus on ground state properties of neutral closed shell compounds for which neural networks basically were, so this data set was designed, ANI data set. Then the accuracy is especially excellent, so we reach chemical accuracy. Remember that slide from 10 years ago, that was our goal, to reach chemical accuracy for thermochemical properties, and we do achieve it now. And if you look at geometries, they are really excellent. So we can get geometries for big molecules. We can compare to small molecules for which we have very accurate experiments, because for big molecules it's hard to get from gas phase experiment, but for small molecules we do have. And if you compare the triple bonds, as for example here, very nice, and other bonds are also good. So this method is really giving you coupled cluster accuracy for many geometries up to sometimes sub-picometer accuracy. If you talk about, I'm specifically mentioning triple bonds because the next example we'll talk about these conjugated compounds, polyions, which have these triple bonds. And these systems is known to be notoriously difficult for quantum chemistry and also experiment. So it's very hard to synthesize it. It's very hard to treat it theoretically. For example, many popular DFT functionals break down. They predict a completely wrong structure. You need something like couple cluster to recover the correct structure. Some DFT functionals work for this too. But it's kind of a gamble, so sometimes it works, sometimes it doesn't. So you want to do really coupled cluster, and the AIQM1 can do this very fast. For this molecule, you cannot really do coupled cluster, and DFT is not accurate enough, so you really don't know what is the bond length for this molecule from theory. It's just too many atoms. But when we optimize it, we find that the triple bond length here is around this 1.2 something. And when we looked at the experimental data, we had a big disagreement actually for our standards, so it was too much. And usually theoreticians are suspicious about theoretical methods if there is disagreement with experiment. But when I look back at triple bonds, they are very good, so there is no reason why our method should not treat triple bonds correctly. And that's why we basically looked at the literature and found that it's known from 70s that the models used in X-ray identification of the structure were just not good for triple bonds because they were based on independent atomic model, which looks at basically electron density, and electron density is very, very high in the middle of these bonds. So it underestimates bond length. And experimentalists just didn't notice it because it's kind of standard tool, right? But that's known from 70s and kind of a bit forgotten. So now we ask experimentalists to remeasure all these crystals because they can use a better density. So they don't need to use the independent atomic model. And when they remeasured, the experimental bond length is now similar to our prediction. So that makes a difference going to coupled cluster instead of trying to target DFT. And this is very important to get proper answer for the proper reason. And only if you have this kind of coupled cluster accuracy, you can really be confident in results. And I will show you more examples later. So this method is also not a machine learning potential, so it can treat different properties for which it was not trained for. So this is quantum mechanical method, and it just improved with neural networks. So as a quantum mechanical method, it can be used for charged species without being trained on any charged species. Of course, now there are better methods like AMNet, which can treat charged species and spin states and so on. It's also quite good for non-covalent interactions, especially for water, for which many methods struggle, and for heat formation, which also with a smaller scaling, so it allows you to run heat formation very, very fast, faster than with DFT and faster than with composite methods and coupled cluster. And the advantage for this is that we can really get very accurate heat formation, so that's towards chemical accuracy. We target 1 kcal per mole accuracy without taking any shortcuts. You don't use any tricks like people who use DFT, they know that DFT is actually terrible for heat formation. So why DFT works for reactions and so on? Because we always look at relative energies. But actually DFT is really terrible for, at least popular functionals, really terrible for the atomization energies and heat formation, and people try to improve them with composite methods, so they run single points and so on, or you can use some isodesmic schemes and so on. So there are many shortcuts to make DFT work, but we don't need to do all of these shortcuts. We just calculate total energies, calculate atomization energies, calculate heat formation directly from our result. No shortcuts here taken. And here you may notice that when we take this without outliers, and outliers basically uncertain predictions. So AIQM1, it's a kind of semi-empirical method. On the other hand, it's also data-driven semi-empirical methods. And it's a data-driven method. It has uncertainties estimates. And the major question is how you judge whether uncertainty is too high or not too high. So you need to have a very stable predictor whether the method is good or not. And for quantum chemistry, we just don't really have a very easy way to do it. For this, we do. And we just took at the molecules for which we know it works quite good. And then we estimated the deviation between neural networks, and then we can estimate how much the deviations can vary, so that we still get confident results. And if we look only at the confident results, then so we know that results improve. And for others which are not confident, so there is some room for improvement. We can train on more data and so on. But at least it gives you some information whether it's applicable or not. Still, you can argue there are some outliers, like not really 1 kcal per mole, even G4 here struggles. And what we found is not because methods are bad, it's because, again, experiment is not very good. So I always challenge experiment, because experiment is done on approximations. There are many uncertainties, while with theoretical methods, we are already able to treat many systems with high accuracy. So for these systems, uncertainty of the AIQM1 is very low. We know it's confident prediction, so we are pretty sure it's correct. To make it even more confident, we compare to much slower methods, which run for hours or days. And then we see that agreement between our methods, which runs in minutes or seconds, is in the same agreement as G4, while there is a disagreement with experiment 4 kcal per mole. It's too much. So what we found out that these experimental data were too old and they were wrong, and later they were revised in the NIST data set with newer experimental values, which are much closer to our theoretical predictions. So this way, when the methods are trained on high accuracy data and they are transferable, we can with confidence verify, experiment, and even correct it. Now these methods are general purpose, so you don't need to retrain them for new systems, and we actually use them for applications without any fine-tuning. So we believe in the methods, and we use them already for applications, computational chemistry applications. Like, for example, Tobias Schaub contacted us to investigate these very nice cycloparaphenylines. And you see that we get this structure much faster with AIQM1 than with DFT, while correspondence to X-ray structure is even closer. But then we can treat much larger systems which we don't even want to use DFT anymore. So we can add some hosts, fullerene, and inside the cycloparaphenylene. And again, it's just a matter of minutes to get the result done. And that's already useful for both computational chemists and experimentalists. And beyond that, as a semi-empirical methods, we can do excited state simulation. So we had also a very nice presentation by Dral, who was showing how to use semi-empirical methods for excited states. And our methods can treat it too, because it has quite good accuracy for vertical excitation, but it also has implementation of analytical gradients. So you can optimize excited state geometries. And that can be useful for simulating and exploring materials, fluorescent materials, or even photocatalysis. And again, accuracy here to compare with TD-DFT, some of them not the best, but that's something very similar. So 0.35 for this data set. We can do geometry optimizations with it. We can do also dynamics. And here is so one way to use this method is for large systems, but you can also run long dynamics because it's fast enough to do this. And the benefit is if you run long dynamics, here ground state, then you can extract MD spectrum for infrared spectrum from it. And when you do this, you obtain much better accuracy in comparison to experiment than you do with other semi-empirical methods like GFN2XTB or even with DFT, just because we have a better potential. And we also can do infrared simulation spectra because we have dipole moments, so we can really simulate the infrared spectrum without making any modifications to the method. We also tested for barriers performance, and barriers were not in the training data. So Oles showed in the first presentation that you can get very nice barriers already with his methods, but this method was never trained for this because there was nothing in the data set. Still, the accuracy even for barriers is remarkably much better than from the baseline semi-empirical method. So we improve semi-empirical methods without doing anything in the data set. for barriers. And the geometry optimization of transition states, which is a major application of semi-empirical methods actually, is really very fast. It's even faster than GFM2XTB. And of course, it's much faster than DFT. While the accuracy, if you do later, for example, couple cluster calculations on top of these geometries, you can get very good accuracy with these methods. So this is one way. Now there are many, many machine learning methods, and looking also at AIQM1, it's only one of the methods. So we saw in this conference how many developments are in the field, and that's on the one hand great, on the other hand it presents a major challenge. Also Reinhard was talking about this, how do we combine all these new developments, right? And there is a whole zoo of machine learning potentials. I don't show all of them, but maybe you can find your potentials there, maybe not. But this zoo is growing very, very fast. And the problem with this zoo is that there are just too many. All of them have different input formats and scripts and so on. So what we've done, we couldn't implement everything. We don't even try to implement everything. It's impossible. We categorize them in some specific classes, like kernel methods, neural networks, different descriptors, fixed, learned, so message passing, whatever. And once you have this, we implemented some of these representatives of each class of the methods, and you can use basically the same input, just switch the name in the input file, and then you can train your model. And this is implemented in the MLatom 3, which just celebrated 10 years. So this comes with a Python API, but it also has a simple like text input file for many computational chemistry users. And the nice thing about all this software is that we support different models. So you can train your own model and plug it in. And you can train it with MLatom. So basically, we provide this functionality. If you provide the data, you can train it. And you can also use many of the pre-trained models, like ANI models. Also, you can use pure DFT or ab initio methods, semi-empirical methods. Or you can combine them together. You can use these AIQM1 methods, for example. All of this functionality is in one package, and then you can use it to do your simulation. So you can, with any of these models, or your own model, you can do this geometry optimizations, frequency calculations, molecular dynamics, generate spectra, like infrared spectra, UV spectra, do thermochemistry calculations, and so on. And I will show you some examples. Of course, all of this is only possible because we do it open source and we use open source software. So we benefit from open source software, we also give back open source. And I think this is a major change in the community, which is very nice. I really like to see that so many open source packages appear. For example, for semi-empirical methods, we use Sparrow, by Markus Raya, and then Mendio by Walter Thiel, and XTB by Grimme. So it's very nice to have all this software available. And beyond that, we also provide cloud computing service so that you can run these simulations based through the web interface. Then you don't need to install all of it, because you see, like, there are many software. If you want to make it work, you need to install all of them, which is quite a mess. So now if you have this XACS cloud computing, just go to the website, you put your input file, choose your methods, and then it will automatically run the simulations with pre-installed software for you. This is free of charge for academic users, so no problem about that. And quite decent CPUs there. So we are very lucky to collaborate with many people who contribute to this project. And I was showing you that we can generate some spectra. And I was showing you that this is going via the way of improving QM methods. So this was example for molecular dynamics, which you can generate infrared spectra from. But we can also do this for like non-adiabatic dynamics, and then also generate spectra from non-adiabatic dynamics, like two-dimensional spectra. We can also do high-precision UV spectra, so not just based on one point, but we can generate ensemble of geometries and generate very precise spectra. Or we can go directly to predict spectra, because machine learning doesn't care what it's learned on. And if you have very nice experimental data set, which we didn't have for this project, but we assembled ourselves. And the nice property of two-photon absorption is that you absorb 2 photons, you get high energy photons, so which is very useful for up-converting laser and many other applications. The problem is how to find this compound. So we did this training on experimental data, and then you can predict for your materials. We also found some nice materials with this approach. You can also run dynamics with improved quantum mechanical methods or surrogate models, so that's very standard. But what I want to show you, that's the last topic, that we can think about it a bit differently, right? So what we always do in dynamics, we take the previous step or steps, depends on kind of dynamics, and then we predict what happens as the next step as a function of the previous steps. We do not need to do this any longer because with neural networks, we can take a very big shortcut. We can predict the points at time as a function of time directly. We don't need to do this stepwise propagation, which is incremental, plus it's also will give you different results based on the time step. And we showed it for quantum dynamics. I will not show you much about this, I just show you concepts here. But another concept is that you can predict the whole trajectory as a function of some parameters, simulation parameters. So we also showed it for quantum dynamics, so we call it one-shot trajectory learning. And now we extend these concepts to molecular dynamics because I am a chemist, so I like to look at a molecule. And I like to see how a molecule actually behaves. And for molecular dynamics, that is very slow to simulate, but with our models, which we now developed for predicting nuclear coordinates as a function of time, this concept is so powerful because you can also take derivatives of this analytical neural network, right? And then you get velocities, you can take more derivatives, you can get accelerations, you can recover forces. So this is basically how we should do and treat molecules because molecules are four-dimensional space-time objects. And with molecular dynamics, you try to recover it, but it's much slower if you try to do it directly. So these models, if you then unravel them in time, they will give you molecular dynamics much faster than you would do with classical MD. So that's basically almost it. So we do provide workshops for all this software. We, of course, have started this very nice symposium, which I will now talk about after the questions and answers, because there will be announcement of the next one. So thank you very much for your attention.
The last speaker got a little more time than the rest, but I think he deserved it because it was quite rich. So there is a question over there.
Thank you for your presentation. Is AIQM1 the only semi-empirical method to reproduce the correct structure of cyclo 18 carbon? And can your method reproduce other carbon rings, such as cyclo 10 carbon?
Yeah, so one thing about doing method development is that there are many applications, right? So yeah. We have a method, you can try it if it works. We work now on different systems, not cyclo systems, but other systems in which we are more interested. But this method, again, is available for computational chemistry use, so you can run it for these systems. So we didn't test for everything, of course. Probably the more it's used, the more limitations will be discovered, right? Yes. Yeah, thank you.
Yeah, so the cyclo 18 carbon, is it included in the training state?
No.
Oh.
Nothing of it was in the training state.
Yeah, it's thank you very much.
Thank you, Pavlo, for a very nice talk. So you said it was a, let's say, general purpose method, which doesn't require the training, but I understand it's also limited with respect to the different elements. So now it's only organic, like carbon, oxygen, nitrogen, hydrogen. So how much extra work would it take to expand this to, let's say, the whole periodic table like you can see for XTB or for PM6, for example?
Yeah, that's a good question, because of course we want to extend it, so we are working on it, and luckily for us, it's not only our efforts, it's the effort of the community. So everyone is interested in more elements, so more and more people generate data for more elements. There are many data also available publicly, for example, again, OLED showed for, I think, 14 elements. So we'll benefit from this. So that's why this question is basically to the whole community. When do we have enough data? It's only now matter, if we have this data, we retrain, we have a better model, and we already started doing this for the available data sets. So we're extending it. Luckily for us, it's not our own single group effort. It's really effort of the community.
Okay, thank you. And I had another question as well. So you have these like polygenic systems and so on. And I guess the failure for DFT is also depending on how much Hartree-Fock exchange
right.
that you include. So I guess your method is based on a semi-empirical method, which is like Hartree-Fock based, right? So
yeah, this one is Hartree-Fock based. I don't know what will happen if you use, for example, DFTB based or XTP based. That will be a good question, actually.
Okay, thanks.
Thanks for the nice presentation, and also thanks for organizing, of course. I was very intrigued by the, I suppose, adaptive time step machine-learned integrator.
Okay.
Could you perhaps comment on the properties of this integrator? Like, for example, often symplectic integrators are desirable. Is this particular one time reversible, for example?
Yeah, that's an excellent question. So we try to look at physically motivated, basically, this is physically motivated neural network, because we try to include correct physics in it. At the moment, we included the requirement that it should satisfy total energy conservation. But as any new method, so you know how much work is done in MD for different algorithms. Now, when you have first algorithm of MDs and you want to extend it to all these thermostats and other things, the same problem will be with our method. So, okay, we have the completely new way to do dynamics. It's actually more than dynamics. It's a four-dimensional model which you can use for other things. But if you want to treat it as a dynamical method, then you also need to think how you will design an algorithm to use it, for example, for NVT simulations. So, yeah, so that's why it's still, since it's very new, there will be lots of work on this, and we are working on parts of this. That's why we include it in the training, so it's a loss function, so we make the physically inspired networks to respect the basic physical laws, like also conservation of angular momentum and so on. Okay.
Thank you.